Good afternoon all. I am Dr. Deepak Yadav, and today we will discuss the next topic of our wave propagation lecture. This is in this we will study about the sky wave propagation. So this is a little introduction. What is wave propagation? So wave propagation involves three different type of propagation, that is ground wave propagation, space wave propagation, and sky wave propagation. In the previous lecture, we will discuss this. We already discussed the space wave propagation. So in this lecture, we will going to discuss this sky wave propagation. So what is sky wave propagation? In case of sky wave propagation, the frequency is very much fixed over here. This is 2 to 30 megahertz, and in sky wave propagation, the wave that is transmitting from the Earth's surface is going into the very upper layer of the atmosphere. This is ionosphere. Due to the very large intensity of the sun rays or cosmic rays, this ionosphere, the air in this ionosphere became ionized, like oxygen gas is converted into O minus minus and removed to electron. And due to this ionization of different gases, this ionosphere is filled up with lot of electron. So the electron density of this layer is very large compared to the lower layer of the atmosphere. So when the wave is entered from the transmitter to this ionosphere, there is a phenomenon known as reflection, and a phenomenon known as total internal reflection is take place, and the earth and the wave is coming back to the earth. And if there is a transmitter over here and then there is a receiver over here, we can receive this signal without any reflector in this space. We can reflect this wave due to this ionosphere and receive at the receiver. So this is the overview of sky wave propagation, in which we use the property of reflection of the wave from the ionosphere to reach up to the receiver, and this distance is very large. It is in thousands of kilometers in case of sky wave propagation, because the height of the atmosphere or the ionosphere is again very large compared to the Earth's surface. So we can easily travel a large distance from the transmitter to the receiver with the help of these waves. This special phenomenon is take place only in the range of from 2 megahertz to 30 megahertz frequencies. So these are some description of different layer of the ionosphere. So the ionosphere exists between 30 miles to 250 miles, and we use this ionosphere for sky wave propagation as well. So these are the different layer of the Earth atmosphere. The primary layer, the first layer from the Earth's surface, the first layer is the 15 kilometer from the Earth's surface, and this is known as troposphere. And space wave propagation is take place in this space wave or ground wave propagation in this part of the atmosphere. Next is the stratosphere, up to 50 kilometer, and there is no communication take place. Only sky waves goes from in and out from this stratosphere. And the last layer is the ionosphere, which is above the stratosphere, and it is from 50 kilometer to 400 kilometer in the space, which is again made up of different layer like D layer, E layer, F1 layer, and F2 layer. So when the wave enters over these layers, the density, electron density of these layers are different, and as the frequency changes, the reflection property of these waves is changed according to the incoming frequency, and take the reflection and provide the reflection to the incoming wave from the transmitter to the receiving antenna. Then this is the structure of the ionosphere. As we already discussed, there is two layer, which is F1 layer, F2 layer, and the lowest layer is D layer. D layer is from 50 kilometer to 90 kilometer from the Earth's surface, while this is the structure. This is the D layer from 50 kilometer to 90 kilometer from the Earth's surface. From 90 to 140 kilometer, we have E layer. From 140 to 250 kilometer, F1 layer, and from 250 to 400 kilometer, this is F2 layer of the ionosphere. This is troposphere, which is 10 to 15 kilometer only from the Earth's surface. And there is one more layer in between over here. This is a stratosphere, which is of very less used for the transmission of the signals. So these are the description of these layers. Now we have to find the refractive index of the ionosphere so that we can calculate how much reflection of a wave field when it enter into the different layer of the ionosphere. So for doing this, we goes to the very basics of the physics, that is the field radiated by the field that is transmitted in the form of electromagnetic signal. This E is equal to Em maximum value sine of omega t. Now if we see the amount of force that is applicable over the electron, F is equal to charge of the electron into the electric field. So F is equal to minus E of E, and we again know the another formula, force is equal to mass into acceleration, F is equal to ma. So we have the force over the electron, that is equal to minus E of E, and mass of the electron is small m, and the acceleration is the differentiation of velocity. So we take the velocity of the electron v over d over here. So the total acceleration is dv over dt. So this dv over dt is the acceleration. So if we calculate dv over dt, this is equal to minus E times of electric field into electronic charge over the mass of the electron. Or we can say dv is nothing but this is equal to this. Now if we take the integration over this value, we can find the velocity of the electron in the particular layer in terms of electric field applied over this electron. So now we take the integration, we have the velocity that is equal to minus E by m, Em sine omega t. This is the value of the electric field. So if we take the integration, the velocity of the electron v is equal to Em cos omega t by m into omega, where omega is the angular velocity of the applied electric field. Now if we see the velocity of the electron is influenced by two type of it generates two type of current. If the electron is drift, then it provides a drift current, and another thing is when the electron is diffused from one layer to another layer, then it provides the diffusion current. So there is one formula for the current that is provided by the electron. It is given by J, current density Je is equal to minus N. N is the number of electron, E is the electronic charge, and V is the velocity of the electron. So it is equal to Ne, and V, as we calculated, V this over here, we put this value over here, then V is equal to dm omega Em cos omega t. So this is the value of the current density due to the electron, and it is given by this. Now for the displacement current, or we can say the diffusion current, what is the value of this is the value of Gd, that is nothing but d over dt. With this d is the flux density generated due to the field applied. Then d over d is equal to epsilon naught times of E. This is the formula, d is equal to epsilon naught times of E, and we have the E is equal to Em sine omega t. Now the diffusion current, the previous one is drift current, the diffusion current or displacement current is nothing but Jd is equal to epsilon naught Em omega cos omega t. Now the total current flowing due to the electronic charge density, Jt is equal to Jd plus Je, or this is nothing but epsilon naught Em omega cos of omega t, this value and this value. Now the total current density that is flowing due to the displacement current or drift current of the electron is given by this equation. Now if we compare this equation with the equation number 6 over this, and if we compare, we see this epsilon naught value is changed by some amount, and this is epsilon naught minus n electronic number of electron in that particular layer, E square by m omega square. So now your new epsilon is became this. If we take the epsilon naught common, we have the value that is equal to this. So your new epsilon of the layer is became epsilon r, that is permittivity, that is epsilon r is equal to epsilon by epsilon naught, and if we divide this value by epsilon naught, we have the effective refractive index or effective permittivity of the layer in which the electron is nothing but 1 minus n e square upon m omega square into epsilon naught. Now, for the refractive index of any layer of any two layer, when there is an interaction between two medium, the refractive index, if we have the epsilon 1 over here and epsilon 2 over here, this is equal to n is equal to refractive index c by v, where c is the velocity of the wave in the one medium, while v is the velocity of the wave in the another medium, and this velocity is proportional to c is equal to 1 upon under root of mu naught epsilon naught, and v is equal to 1 upon under root of mu into epsilon. So if we put this value over here, so v is equal to under root mu epsilon, c is equal to under root mu naught epsilon naught, and if we put this value in these terms, epsilon naught epsilon r, so these values get cancelled out, and we have the refractive index is proportional to mu r into epsilon r. This mu r for the medium is again constant, because there is no change in the magnetic field strength, only change in the this dielectric constant. So mu r is again, we are consider mu r is equal to 1 over here. We find that this mu r is 1. Your n, this is nothing but n is equal to under root of epsilon only over here. So the refractive index of the layer having the n number of electron in the layer is equal to under root of epsilon r, and is equal to under root of 1 minus n e square upon m omega square into epsilon. Okay, so if we put the value of these constant, like charge of the electron is 1.6 into 10 to the power 19 m, mass of the electron 9.1 into 10 to the power minus 31, and epsilon naught is this. If we put these values, we find the refractive index of the layer is nothing but it is under root of 1 minus 81 n. N is the number of electron in that layer divided by frequency. So we can see over here that the refractive index n is proportional to n and is inversely proportional to the frequency. So as the frequency increases, refractive index decreases. As the electron density increases, again refractive index is increased over here. So this is the formula for the particular layer having the number of electron n in this layer. So the wave mechanism of the wave propagation, how this reflection take place. The refractive index of the layer is nothing but under root of 1 minus 81 n by f square. In this case, ionosphere will be behave like a rarer medium. So when the wave penetrate from the stratosphere to the ionosphere, it seems like it is going into the rarer medium. So when the wave is enter from the denser medium to the rarer medium, the wave goes away from the perpendicular over the surface of these two medium. So wave get little reflected over here. Then again, this is again a second layer is again rarer than the previous layer. It got again like this, and at certain point it get a total internal reflection. So you can see if the incident angle is I and reflection angle is R, this reflection angle is larger in compared to the incident angle, because wave enter from here to the rarer medium. And this is the formula of the reflection. N is equal to sin I by sin R. It is equal to this, and this is equal to this. So these are the different layer of the ionosphere: N1, N2, N3, N4, N5 and N6 having different number of electron density. As the electron density increases, why the electron density is high over the upper layer? Because most of the radiation is coming from outer space, from the sun or from the cosmic waves. So these waves are having very high energy like gamma radiation, X-rays, ultraviolet rays. So whatever the amount of air over here, it gets immediately ionized into H plus electrons, O minus minus electron electron. So the maximum density of the electron is in this range. Then it goes down 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 up to D layer. So these are the refractive index. These are the different layer having different number of electron density. Electron density is increases in this way. So as the wave enter into the ionosphere, due to the increase in the electron density, the medium get rarer and rarer, and the wave start going away from the perpendicular in this way, and at that point it get into the total internal reflection and coming back to the denser medium and at the receiver over here. If we consider mu is equal to 1, which is in case of atmosphere, it is equal to 1 only. Now there is multiple term that is connected with this total internal reflection and this sky wave phenomenon. The first one is the critical frequency. Critical frequency is nothing but that frequency in which if we send the wave directly vertically above from the ground to the ionosphere, and if this wave get reflected back to the earth, so the maximum frequency which enters the ionosphere vertically and reflected back to the earth surface is known as your critical frequency. So critical frequency is represented by Fc, and it is for the vertical entry of the wave into the ionosphere. So now critical frequency, to calculate the critical frequency, we have the entrance angle I is equal to 0, and for the I is equal to 0, if we put n is equal to sin I by sin r, if the sin I is equal to 0, so this became 0, and we can write this under root of 1 minus 81 n by f square is equal to 0. In this case, this n is represented as n max, maximum number of electron density, maximum number of electron for the vertical incident of the wave, and f is become Fc, that is critical frequency. So if we calculate this is equal to 0. This one is coming over here. Fc is equal to under 81 by n, or 9 under root n max. So the critical frequency for any layer is represented by n 9 under root n max, where n max is the maximum electron density of this layer. So the maximum frequency that is reflected back when vertically incident is directly proportional to the number of the electron in that layer. So this is represented as Fc is represented in megahertz, and this is the formula for critical frequency. The another term is the maximum usable frequency. So what is the maximum usable frequency? This is the frequency when the wave is not incident vertically over the surface, over the different layer of the ionosphere, but having some angle. So the maximum frequency that is reflected back from the ionosphere when the incident angle is not vertical, then this frequency is known as maximum usable frequency. So for calculating the maximum usable frequency, this I is nothing but the incident angle, but for reflecting back, R must be greater than this 90 degrees, so that the total internal reflection take place. Then n is equal to sin I by sin r. So sin r sin 90 is equal to 1, then sin square I. If we take the square on the both the side, we have this. On calculating, we find this is equal to sin square I is equal to this 1 minus sin square I. This is equal to cos square of I. So cos square of I is equal to Fc square mfuf. Take the under root both the side, and we get f muf is nothing but Fc sec of I, where Fc is the critical frequency of the layer. So the maximum usable frequencies again depend on the critical frequency and the incident angle of the wave. For this critical frequency, the incident angle is already 0 degree. So we can write f muf is nothing but 9 times of under root n max. This is the maximum number of electron multiplied by sec of incident angle. So this is known as the second law. due to this sec term over here. So, the maximum usable frequency is equal to fc sec of I. Now, how these this ray path take place? So, if the incident angle is very large, like very high, wave get a little reflection and then goes into the sphere as the ionosphere is end over here. So, the total internal reflection does not take place and the wave goes into the space. In the second case, when the incident angle is little low, the wave goes into the ionosphere very deep and from the upper layer it get reflected back to the earth surface. So, the distance between the transmitter and receiver in this case is very large. The third one case is in this case when it is reflected from the very lower layer of the ionosphere and reflected back, and this is the minimum distance because this is reflected from the very lower layer of the ionosphere. After there is no ionosphere, so there is no reflection. So, this is the minimum distance that is not broadcasted or not covered by this transmitter, because the minimum distance after which the signal start receiving is from this point to this point. So, this is known as the skip distance, that is with the help of skywave propagation. In this area, we are not able to broadcast any station due to the minimum skip distance over here. If the angle goes again down, then we can cover this area by these multiple waves. So, these are the different ray path when a skywave communication take place. So, this is the description of these waves. Next is the virtual height. So, if the wave is going from here to here and there is a reflector over here, maybe a satellite or maybe a reflector over here. So, the wave, in the absence of ionosphere, the wave goes like this from the reflector and goes back like this. But there is no reflector over here, but there is a layer of ionosphere and there is a multiple reflection due to the different layered structure. So, this wave is actually follow this path, this curved path due to the reflection and goes back to the earth. So, this is the actual height attained by the rays, but it seems like it is there is a reflector and this is the virtual height that is followed by the rays over here. This virtual height is known as the virtual height. So, these are the term that is virtual height that is described over here, and thank you for this lecture.